Hello everyone. So today we continue our discussion with the branch and bound algorithm for integer programming formulations. And today we will start considering the binary variables. How do we apply a branch and bound algorithm to solve a problem that includes binary variables? The main idea is exactly the same with general integer variables, but this time, since a binary variable can only take two values, 0 or 1, while branching, instead of including a inequality as a constraint, we will just fix the value of this decision variable either to 0 or to 1. So the main idea is the same, but there are some few differences. So we will solve some examples and try to understand how we can apply branch and bound algorithm for binary variables. So let's start. Before starting our discussion with the binary variables, let's first make an example to improve our understanding on the branch and bound algorithm and how can we fathom nodes with respect to the bounds. So for this purpose, let's consider this example. It says that the following tree shows a branch and bound search. Okay, at this point, let's stop a little bit. Is this branch and bound tree given here? Is it for a minimization problem or a maximization problem? Can you understand it? So please think a little bit, if you like, by stopping the video. Okay, so if you say this is for a minimization problem, then you are right. In fact, in our previous video lecture, we talked about this while considering these parent bounds. We said that the parent of children, so the parent node, always provides a better solution than the children. Okay, so parent provides always a better solution. So this v tilde here represents the objective function value. Okay, so this node 0, you see it's the parent of node 1 and 2, and its value is 55. And you see its children has one child has 60 and the other child has 69. So 55 should be a better solution than this. Is it better if this is a minimization problem or if this is a maximization problem? Of course, if this problem is a minimization problem, 55 is better than 60 or 69. So by just looking at this branch and bound tree, we can understand that this is a minimization branch and bound. Okay, so we can just delete this part. Okay, there's another question here. Is this branch and bound tree? Is it which kind of search did we follow? Is it a depth first search or a breadth first search? Okay, you should memorize what were these search algorithms. In fact, they identify in which order we evaluate the nodes. Okay. So for this purpose, you need to look at the node numbering. Okay, this numbering gives you the order of evaluating the nodes. Okay, we start with the root node, which is numbered as 0. Okay, then we move to this node, which is in level 1. So remember, this is level 0. The level of root node is level 0. The level of this first children is level 1, and the level of the second children is level 2. Okay, so we started with the root node, then we moved to the first level and considered this one and decided on branching it. Now at this point, if you consider just after we evaluated this one, this node, and this node is open. And among these open nodes, we selected this one. Not this one, but with this one. So we considered the node at the upper level first. And since we considered a node at the upper level, this means we followed a breadth first search. Okay. So if it was a depth first search, then the numbering should be like this. This node should be 2, then this node should be 3, then this node should be 4. Okay. But since this is 1 and this is 2 and then this is 3, we immediately understand that this is a breadth first search. Okay, so these were some previous stuff. Let's continue. As we said, this is breadth first search. It's not related with the question, but an addition to this question. Okay, it says that in this branch and bound search, we processed 4 nodes, 0, 1, 2, 3. We already processed these nodes. Okay, and we discovered the first incumbent solution. Incumbent means, I'm going to talk about it in a few minutes. Incumbent means the best integer feasible solution. Okay, best integer feasible solution. So we have this best integer feasible solution in this node 3. Then it says that these nodes alpha, beta, and gamma, they are not explored yet. They are open. So we just finished exploring this, and we will continue with this, and we fathom this node by solving, because we get an integer feasible solution. Now the question is this: depending on the objective function value that we obtained here, which one of these nodes can we fathom because of bound? The question is this. And the question has 2 parts. It says that, okay, initially, let's consider that the incumbent solution that we obtained in node 3 has an objective value of 80. Okay. Then the question is, can we fathom any one of the nodes, unexplored nodes, alpha, beta, or gamma with this one? Okay, how can we decide on this? We should consider like this. 80 is the best. This is a minimization problem, we understood it. And we have a solution with objective function value of 80. Then let's look at alpha initially. What is the best possible objective function value that this alpha can provide? In order to learn this, we should look at its parent. And the parent objective function value is 60. So this 60 for a minimization problem gives a lower bound for its child. So this child can provide a solution with 60, and this is the minimum. This is the best solution that it can provide. It can provide 60, it can provide 65, it can provide 120, it can provide infinite. We don't know. It can be infeasible. But the minimum possible value is 60. It means that there is a possibility here to obtain a solution which is less than 80. So we cannot fathom this node alpha because of bounding, because there is a possibility of getting a better solution. Okay, so we cannot fathom alpha. What about beta? Let's consider it. Again, we have a solution with 80 in our hand, and the question is, can this node provide a better solution than 80? In order to understand this, again, we will look at its parent, and its parent's objective function value is 69. It means that the beta can provide a solution with 69, with 70, with 80. We don't know, but there's a possibility that it can provide a solution less than 80. So we cannot fathom beta as well. What about this gamma? Since the parent of gamma is the same with beta, our conclusion is the same, and we say that we cannot fathom any one of the nodes. So in this first part A, Okay, if the objective function value that we obtain in node 3 is 80, we cannot fathom any one of the nodes, alpha, beta, gamma. We cannot fathom them. Let's consider this part B of the question. Now it says that if the objective function value, integer feasible or incumbent, objective function value that we obtain here is 63, then can we fathom any one of those nodes? Let's make the same reasoning. Okay, alpha, let's look at alpha. When you look at its parent, it says that alpha can provide a solution with a value of 60. Although this 60 and 63 are very close to each other, still this 60 is less than 63. So there is still a potential, there is still a possibility that we can get a solution which is less than 63. So we cannot fathom alpha, we need to explore it. What about beta? Look, its parent has an objective function value of 69, sorry. And this is the best, this is the minimum. Since this is the minimization problem, best means minimum. This is the minimum that this beta can give you. And we already have a solution of 63. We already know a good solution, a better solution than this 69. So why do we consider evaluating beta and gamma? The gamma also has the same parent. So the best objective function value that it can provide is 69, but we already have a solution with 63. So it means that we can fathom beta and gamma. So if we obtain an incumbent solution of 63, then node beta and node gamma can be fathomed at this point, and the reason of this fathoming is because of bounding. Okay, so this is a use of parent bounds to fathom unexplored nodes without exploring, before exploring them and losing time or spending time on them. Now let's consider two definitions that we will make use in the branch and bound search. The one is I already talked about, which is the incumbent solution. An incumbent solution means the best solution that you find until that time of the branch and bound search, until that node of the branch and bound search. So we will make an example and I will show you how we identify these incumbents. But whenever you come up with an integer feasible solution, if it is better than the previous integer feasible solution that you identified, then it becomes your incumbent solution. And we always keep this incumbent solution in the memory. So whenever the branch and bound algorithm stops, the incumbent solution that you identified is the optimum solution that the branch and bound procedure provides. Okay, so incumbent is the best solution that you identify during the branch and bound search. Okay, the second thing is the gap. You know, these integer programming formulations may take a lot of time to solve. And while, for example, if you are going to solve your projects in Cplex OPL, again for the problems with larger size, when you try to solve it, it will not solve it immediately. Okay, then when you look at in Cplex OPL, the engine log tab, you will see that some numbers are flowing in the screen. And on the rightmost column there, you will see some percentages. Those percentages, in fact, show you the gap, which is this one. And in fact, it shows you the percent deviation of the best found solution, which is the incumbent solution, from the best possible solution, which is the bound. If this is the minimization problem, best possible is your lower bound. If this is the maximization problem, best possible is your upper bound. and the lower and upper bounds are found from the relaxations, remember, or from parent bounds. Okay, so then how do we calculate this gap value? As we said, it's the percent deviation from the best possible solution. So it is best found, which means incumbent, minus best possible, which is the bound, and this is in absolute value because this gap value is always positive, divided by the best possible that you can find from this branch and bound search, which is your bound. And when you multiply this by 100, you come up with your percent gap value. Okay? If your problem is a minimization problem, then the best found value or the incumbent value is your upper bound, in fact. And the best possible value is the best that you can obtain at the end of this search is your lower bound. So this equation is in fact upper bound divided minus lower bound divided by lower bound. But if this is a maximization problem, okay, again, best found minus best possible. In fact, best found this time is your lower bound, and best possible is upper bound. But since we take the absolute value, this difference doesn't make a change. Okay? Divided by upper bound this time, because the best possible value for a maximization problem is the upper bound. So the difference between minimization and maximization is the denominator. In minimization, you have lower bound. In maximization, you have upper bound. Okay? So this is how we calculate the gap. We will make examples to show you how we calculate these. Okay, now we are going to solve an example with binary variables, and I will show you how to solve integer programming formulations with binary variables. So this will be a complete branch and bound tree, and as well as I will try to write the lower bounds, upper bounds, the increment solutions, and the gap values at every iteration. Okay, so please watch carefully this example. It is a very important example to understand. Okay, so what's our problem that we want to solve? Our problem is a minimization problem. Basically, we have 4 variables. All of the variables are 0 or 1, binary. Okay, so we want to minimize. This is a minimization problem. Then we have one constraint stating that this 3000x1, 6000x2, and etc. should be greater than or equal to 700. Okay. Now, how do we solve this problem using branch and bound? Let's start. Okay, we will start with the root node, of course. Okay, so in the root node, what do? We solve the problem with LP relaxation, and whenever we have integer variables, binary variables, sorry, 0 or 1, we relax them so that they should be in between 0 and 1. Okay, so let me write it here. So let's assume that this is our root node, node 0 here. And how do we find the LP relaxation in this root node? So we say that xi, all these xi are between 0 and 1. Okay, we replace the 0 and 1 restriction to this one. Okay, so when we solve this problem, by the way, in this branch and bound algorithm, I will just give you the solutions of the relaxations. How do we solve it? In fact, you need to use the simplex algorithm to solve it. Assume that we used that simplex algorithm and solved it. Okay, and I will just give you the solution. Okay, so for this LP relaxation, when we solve it, we got this solution. I'm going to represent the solution with x tilde 0. This 0 indicates that the solution in the node 0. Okay, And that solution is 0, 0, 0, and 0.44. You see, x1 is 0, x2 is 0, x3 is 0, and x4 is 0.44. Why? Because we replaced all decision variables with this one, so they can assume fractional values when you solve it. Good. Then what's the objective function value of this solution? We can find it easily by just inserting these values into our objective function. And when you do it, you find the objective function value as 6.12. So this is a tilde shows me the objective function value at this node. Okay, good. So I'm going to write the lower bounds, upper bounds, and the gap values to this table on the right hand side here. Okay, in root node, in node 0. What is the lower bound? Okay, the lower bound is, for a minimization problem, is the solution of the relaxed problem, which is 6.12. Okay, the lower bound is 6.12. What is the upper bound? So for this, you need to remember the branch and bound algorithm. And in that algorithm, we said that if this is a minimization problem, we set the upper bound to infinity, plus infinity. So we have plus infinity. And the gap value for a minimization problem should be upper bound minus lower bound divided by the lower bound. Okay? So here we need to calculate infinity minus 6.12 divided by 6.12. So whenever this upper bound or lower bound is infinity, it means that whenever if you couldn't find an integer solution yet, then we don't calculate the gap. We just state that there is no gap yet. The gap is started to be calculated as soon as you obtained your first integer solution. Okay, now the question in the branch and bound algorithm is, can we fathom this branch, this node? Okay, and there are three reasons to fathom. Can we fathom because of infeasibility? No, we have a feasible solution. Can we fathom because that we obtained an integer feasible solution? And no, because x4 is 0.44. It should be either 0 or 1, but it is not. So we cannot fathom. And can we fathom because of bound? The upper bound is infinity and the lower bound that we obtained here 6.12. So the lower bound is better than my upper bound. So I cannot fathom because of this bound, which means that I need to branch. Okay, branching is done similarly to the previous case. We just branch into 2. Okay, but the most important thing here is this. Which decision variable should I select for branching? x1, x2, x3, they are all 0. So they are in fact integer feasible. The only problematic one is x4. Okay? So I need to branch on x4. And how should I branch? We said that in the previous case, we were adding x4 less than or equal to something, x4 greater than or equal to something. And what are they? Here, I should add x4 less than or equal to 0 to one side and x4 greater than or equal to 1 to the other side because it's in between 0 and 1. So it should be less than or equal to 0, greater than or equal to 1. But we already know from this equation that x4 should be greater than or equal to 0. Okay, if I include this constraint x4 less than or equal to 0, and since I already have x4 is greater than or equal to 0, in fact it means that I am setting the value of x4 exactly equal to 0. Okay, this is very important. And similarly, since from here x4 is less than or equal to 1, if I want to add a constraint saying that x4 is greater than or equal to 1, in fact I am saying that x4 must be equal to 1. Okay, so this is the basic difference between the branch and bound algorithm for the binary variables and for the general integer variables. The difference is either we are setting the values of the decision variables. Okay, so on this side I'm going to write x4 equals to 1, and on this side I am going to write x4 equals to 0. Okay, as I said, we are fixing its value. We are not saying it's greater than or equal to. We are saying that its value is equal to. And in this case, in branch and bound for binary variables, whenever the value of a variable is fixed, it will never be changed. Okay, so we will continue, for example, with this node. In all the children of these nodes, the value of x4 will be equal to 1. And in all children coming from this node, this parent, the value of x4 will be equal to 0. It will never be changed again. Okay, and in order to represent this, if a variable is fixed or free, we use this notation. Okay, so let me write this. We have two new nodes. Initially, I'm not writing their numbers to them. So I need to select one of them. It depends whether we are continuing with depth first search or breadth first search. And again, if they are at the same level, then I need to somehow select one of them. So I prefer to continue with this one with no reason, but we will follow the depth first search. Okay. So that's why I numbered this as 1, but I don't put a number here. Maybe it will be 2, maybe it will be something else. Okay. So here in node 1, we fix the value of x4 to equal to 1. So we represent this in this way. So the value of x1 is free, right? So we represent that free variable with this sign. Again, the value of x2 is free. The value of x3 is free. But the value of x4 is fixed to 1. Okay, so when I write this, you should understand that x1, x2, x3 are free. Free means they are in between 0 and 1. And the value of x1 is fixed to 1. So we solve this problem. What is that problem? In our original model that you can see on the slide, just put 1 instead of x4. And you have a smaller problem. Okay, and solve it. It's an LP. Okay, so using the simplex algorithm, solve it. And when I solve it, I obtain this solution. Let me write the solution. So this is x1, and the solution value is 0, 0, 0. And the value of x4, since it's fixed to 1, it should be 1. Okay, so this is the solution. And you see, all decision variables are 0 or 1. It means that this is an integer feasible solution. That is, this is a candidate solution. And what is its objective function value? Just put these, insert these into the objective function, and you find that the z value is equal to 14. So this 14 is the integer feasible solution. What does it mean? It means that it's my incumbent solution. Okay, the incumbent means this, the best integer solution. Initially, it was plus infinity. Now I found the solution, integer solution, which is 14, and this 14 is better than infinity. So therefore, this becomes my new incumbent solution. Okay, then we need to make a decision here. Shall I continue branching with this node, or shall I fathom it? And of course, we should fathom it. And the reason for fathoming is by integer feasibility. by optimality, you can write any one of these, or by solving, okay, we end up with an integer feasible solution. So we fed them. So let's write these onto the table. In node 1, what is the lower bound? Remember, the lower bound is the best possible that you can obtain from this branch and bound search. And the lower bound comes from the unexplored nodes. Okay, this node is unexplored. And what is the best possible value that you can obtain from this unexplored node? You should look at its parent. And its parent is 6.12. So the best possible that you can obtain here is 6.12, which means that your lower bound is still 6.12. What about the upper bound? Upper bound is your incumbent solution that you obtained, which is 14. Okay, now we are going to calculate the gap value, which is 14 minus 6.12 in absolute value divided by 6.12 multiplied by 100. If you calculate this value using your calculators, you will obtain the gap value, the percent gap value, to be 128.8. This is your initial gap value in node 1. Okay, now what is it? Did we finish the branch and bound search? No, the branch and bound search continues until you finish exploring all the nodes, and we have still one node which is unexplored. Then we should select that one and continue with that one. So I can number it as 2 now. And the solution that I am going to search for this one here is, you see, x1 is free, x2 is free, x3 is free, x4 is set to 0 this time. You see, from here, by branching, I am setting the value of x4 equal to 0. And when you solve this using the simplex algorithm, you obtain this solution: 0, 0.33, 1, and 0. And what's the objective function value? It is 9. When you put this into this solution into your objective function, you obtain this value. Okay, now we need to make a decision. Can we fathom this node, or should we branch this node? And the answer is, you need to branch this node. Why? First reason. Why? Because we cannot fathom it. Because we have a feasible solution, we cannot fathom because of infeasibility. Secondly, there is a non-integer value, which is 0.33. So this is not an integer feasible solution. I cannot fathom because of that reason. And the objective function value of this solution is 9. And for a minimization problem, this is better than my incumbent value, which was 14. So if we continue to explore this, maybe we will obtain a solution with objective function value of 9. So there's a possibility here. So I cannot fathom because of bounding. It means that I need to branch. Then question, branch on which variable? You need to branch on one of the free variables. So x4 is not free. It should be either x1 or x2 or x3. And you should branch on a variable which is not integer, not 0 or 1. So that's x2. Okay. So again, we are going to branch it. In order to use this space suitably, I'm going to branch in this way. Okay. So this x2 equals to 1. Again, I am setting its value on this side. And on this side, I'm going to set x2 equals to 0. It's not important if you write x2 equal to 0 and x2 equal to 1 here. It's not important. It's the same thing. Okay, now let's write what happens in node 2 to here. What is our lower bound? Lower bound is obtained by unexplored nodes. And the unexplored nodes are these two. And the best possible values that these two nodes can obtain comes from their parent, which is 9. Okay, so it means that our lower bound is 9. What about our upper bound? So the only integer solution that we obtained until now is this, which is 14. So our upper bound is that, 14. And what about our gap value? Gap value is upper bound, which is 14, minus lower bound, which is 9, divided by your lower bound, which is 9. And multiply this by 100. And when you do this, your gap value reduces from 128 to 55.6. Okay, so this is your gap value after solving node 2. Then I have two unexplored nodes. I need to select one of them. I am following depth first search, but they are at the same level. So I am going to select one of them and I decide to continue from this node. So I number it as node number 3. Again, so let me write which problem I am solving here. The value of x1, is it fixed or not? So in order to understand if it is fixed or not, you need to go back to your root node from this one and see which variables you have fixed at each step. So in this step, we fixed x2. In this step, we fixed x4. So here, x1 is free, x2 is fixed to 1, x3 is free, and x4 is set to 0, fixed to 0. So I'm solving this problem. Basically, I am putting 1 and 0 to x2 and x4 in the problem on the slide. And I'm solving for x1 and x3 in between 0 and 1. And I solve this using the simplex algorithm. And when I solve it, I get this solution. Let me write, this is the solution in node number 3. Okay, and the solution that we obtain is 0, 1, 0.2, and 0. Okay, you see, x2 was fixed to 1, and in the result it's equal to 1. x4 was fixed to 0, and in the result it is 0. It cannot be something different. And what is the objective function value corresponding to this? You need to write this in your objective function on the model, and you can find 14.33. Okay, now what should I do? Sorry, it's 13. Sorry, this is 13. So what should I do? Can I fathom this one, or should I branch it? There is a feasible solution, so I cannot fathom because of infeasibility. There is a non-integer value x3 because that's why I cannot fathom because of solving or integer feasibility. And the solution that I obtained here, 13, is better than my incumbent solution, which was 14. So I cannot fathom because of bound. It means that I need to branch. Okay, so I need to have two branches. What are those branches? So which variable is fractional? x3. So I'm going to fix x3 equal to 1 and x3 equal to 0. Okay, now I have these two open branches. In total, I have 1, 2, 3 open branches. And let's write what happens in node 3 in our table. Okay, what is the lower bound? Again, the lower bound is the best possible value that you can obtain from the open nodes. Open nodes, these are open, and the best possible that you can obtain from these two nodes comes from its parent, which is 13. And the best possible value that you can obtain from this node comes from its parent, which is 9. So in total, from this branch and bound, the best possible for a minimization problem that you can obtain is the minimum of 13 and 9, which is 9. So your lower bound is 9. And then after finding this incumbent solution, 14, integer feasible solution, until now I didn't find any solution yet. So my incumbent solution is still 14, which is my upper bound. Okay? So when you compare with the previous one, your lower and upper bounds didn't change. It means that your gap value will be identical to the previous one. It is not improved. So you see the gap values always in branch and bound, the gap value starts with a higher value and it goes to down, it reduces, and at the end it will always be 0 because the lower bound is always equal to the upper bound at the end of the branch and bound. Okay, now we have 1, 2, 3 open nodes. I need to select one of them. And as I said, I'm using depth first search. Depth first search. According to this, I need to select a node in the lower levels. So these two nodes are in a lower level than this one. So I need to select one of them. And which one of them? I prefer to select this one. In fact, you could select this one as well. If there is no rule for this selection, you can just select one of them randomly, arbitrarily. Okay. So I selected this one, then I put the next number, which is 4. Okay, which problem I am solving here? Again, you see x3 is fixed, x2 is fixed, x4 is fixed, but x1 is not fixed. So here x1 is free. Let me write on this side. x1 is free, x2 is fixed to 1, x3 is fixed to 1, and x4 is fixed to 0. Be careful while writing this. x2 is fixed to 1. I get that information from here. x3 is fixed to 1 and x4 is fixed to 1. So the path from this node to the root gives me which variable is fixed. And when I solve this, I can represent it like this. The solution in node 4. The value of this solution is 0, 1, 1, 0. Okay. And the objective function value of this solution, when you put it into the objective function of the model, you obtain 17. So this is an integer feasible solution. Good. It means that it's a candidate solution. Now I need to compare this integer solution with my previous best solution, my previous incumbent solution. It was 14. So this is a minimization problem. You always make this reasoning. This is a minimization problem. Initially, my objective function best solution was 14. Now I found a solution which is 17. Which one is better? The previous one is better, right? So we keep the previous one. It means that I am fathoming this node, fathom, and the reason of fathoming is by solving. But on the other hand, since this objective function value is not better than this one, I can also say that fathom by bound. Okay, this is a worse solution. And I don't update my incumbent. My incumbent is still 14. So you can write incumbent equals 14. You can keep this. So let's write what happens in node 4. What is my lower bound? Lower bound comes from the open nodes. This node is open. Its parent, this one. So the best possible value is 13. This node is open. Its parent, this one. Best possible 9. So overall best possible value is still 9. What about the upper bound, which means the incumbent solution? Since we couldn't find a better solution, still it's 14. And it means that my gap value is still the same. It's not improved. Okay, I have two open nodes that I need to explore, you see. And according to depth first search, I need to select this one. And it is numbered as 5. And here, What problem I am solving? Again, x1 is free, x2 is set to 1, x3 is set to 0, and x4 is set to 0. When you compare brothers, let's say these are the children of the same parent, when you compare these two, you will see that only one of them is different. And which one? It is this branching variable. On this side, x3 is 1. On this side, x3 is 0. All others are the same. Okay, so when you solve this problem, what we obtain? We obtain this solution 0.33, 1, 0, 0, and the z value here is 14.33. Now, we need to ask our questions. Can we fathom because of infeasibility? No, because we have a feasible solution. Can we fathom because of we obtain a candidate solution, integer feasible solution? No, because x1 is 0.33. It's not integer. Can we fathom because of bound? Let's see. The objective function value is 14.33. And our incumbent solution is 14. Remember, we are minimizing. For a minimizing problem, 14 is better than this one. So if you branch this and continue, the best possible that you will obtain is 14.33. But you already have a solution with 14. Why do you need to consider? Okay, so that's why we can fathom because of this bound. So fathoming because of infeasibility is easy. The reasoning is easy. Fathoming because of by solving, again you can reason it easily. But fathoming by bound, you need to be careful. If you need to understand the relaxations and the bounds so that you can make this reasoning. Okay, let's fill in the table what's going on in node 5. Okay. What is your lower bound? The best possible that you obtain. It comes from your open node. We have only one open node and its parent is 9, so the best possible is 9. What about the upper bound? The best integer solution that we have found until now, it's still 14. It means that your gap value is the same. You see, the gap value either reduces or stays the same. It can never increase. It either reduces or stays the same. Okay, we need to continue because we have one more unexplored node and we give the next number to it. It's 6. So remember, when we branched node 2, initially we didn't give the numbers to those. If we had given, then this should be 3 and this should be 4. But according to depth first search, what happens? We select one of them and continue from that side numbering, and then whenever we finish all of them, then we return back. So the numbering can be different. Okay. So now in this sixth node, which solution, which problem we are solving? Let's see. X1 is free, so we are going back to the node. X1 is free, X2 is 0, X3 is free, and X4 is 0. We are solving this problem, and when you solve it, I will write in this way, you obtain this solution 0.67010. Okay, and the z value that you obtain here is 9.67. Okay, now we will ask the same question. We cannot fathom because of infeasibility. We cannot fathom because of integer feasibility because x1 is non-integer. Can we fathom because of bound? The best solution, integer solution, is 14. And if you continue from this side, you can obtain a solution with 9.67. For a minimization, this is better. So we cannot fathom because of bound. It means that we need to branch it. Okay, so I'm going to branch in this way. one here, and another one here. Okay, so now we have these two open nodes. It's better to keep the nodes at the same level. So these are in one level, these are in the same, this is in the same, and etc. Okay, so let's write what happens in node 6. What is the lower bound? Lower bound comes from the parent of the open nodes, which is 9.67. What is the lower bound? Lower bound is the increment solution, and it's still 14. And now our gap value is 14 minus 9.67, okay, divided by 9.67. Again, this is for the minimization. If this was a maximization, this denominator would be 14. Okay, you need to be careful. Always keep this in mind. Best possible minus best found divided by best possible. In the denominator, you will always have best possible. If this is minimization, best possible is lower bound. If this is maximization, best possible is upper bound. Okay, so multiply this by 100 and we obtain 44.8%. So you see the gap value reduced. Okay, now I have two unexplored nodes. They are at the same level, so that first search doesn't say anything for the same levels. And of course we need to write on which variables we are branching. We are branching on x1 equals to 1 and x1 equals to 0 because it's only the variable which with a fractional value. By the way, sometimes you will have more variables with a fractional value. So which one will you select? Sometimes we give a rule for it. For example, we say that use the variable which is closer to an integer value for branching. Then you need to select that one. Otherwise, you can select arbitrarily any one of them. Okay, here since we have only one single variable, we select that one. Okay, now I'm going to continue with this node and I'm numbering it as 7. And here I'm solving this problem. Let me write here. x1 is fixed to 1, x2 is fixed to 0, x3 is free, you see from the path here, and x4 is equal to 0, it's fixed to 0. And when we solve it, the solution that we obtain is 1, 0, 0.8 and 0. And the objective function value z is equals to 11. We cannot fathom because of infeasibility. We cannot fathom because of integer feasibility because x3 is 0.8. Can we fathom because of bound? So the best that I found until now is still this one, which is 14. You can put a star to know where you found your best solution. Okay, and this z value says that if you continue from this side, you can obtain a solution with an objective function value of 11. So I cannot fathom because of bound. It means that I need to branch. So I need to branch this one. And I have two new nodes. Let's write what happens in node 7. Okay. Of course, which variable I'm fixing here. x3 is equal to 1 and x3 equals to 0. And what happens here? What is the lower bound? Lower bound is comes from the open nodes. The parent node of these two is this one with an objective function value 11. And parent of this one is this, which is 9.67. So the best of these two for a minimization problem is 9.67. What about the upper bound? It is the incumbent solution for a minimization problem, and it's still 14. It means that the previous gap value is the same. Okay, Now, according to depth first search, I need to select one of these two. I cannot select this one. If this was breadth first search, I would select this one and continue from here. But since I'm using depth first search, I will select one of these. And I will continue from this side and I will say this is 8. Okay, which problem I am solving here? X1 is fixed. You see, X1 is fixed to 1. X2 is fixed to 0, X3 is fixed to 1, and X4 is fixed to 0. Okay, so all these decision variables are fixed. In fact, I am not solving anything. I will just try if this is a feasible solution by putting these values to the constraint and checking if the constraint is satisfied. And I will just put this into the objective function value, and to get its its value. Okay, so when you do this, you see that it satisfies the constraint, and in fact this is 1 0 1 0, nothing to solve. And this z value, when you insert this into your objective function, you obtain 12. And what's our decision here? We need to fathom by solving by integer feasibility, the same thing. Okay, so what are our conclusions in node 8? What is the lower bound? Lower bound comes from the open nodes, and the best comes from here. It's still 9.67. What about the lower bound? We found an integer solution, which is 12. Our previous integer solution was 14. We are minimizing. For a minimization problem, 12 is better than 14. It means that this is our new increment solution. We update the increment. And our upper bound here now is 12, not 14. And our gap value will be 12 minus 9.67 divided by 9.67 multiplied by 100. And its value will be 24.1, I guess. Okay. Then, shall we stop? No, of course, because we still have two more unexplored nodes. Let's continue with them. This ninth one, here we are solving which problem? X1 is 1, X2 is 0, X3 is 0, and X4 is 0. Okay, and then is this a feasible solution? There's nothing to solve, but is it feasible? Just put this into your constraint on the slide. You see that it is not feasible. You cannot obtain a feasible solution. So this is infeasible. So we fathom because of infeasibility. Okay, then let's write what happens in node 9. The lower bound comes from the open node and its parent still 9.67. The upper bound, which is the incumbent solution that you find, and it's 12. So it means that since the lower and upper bounds didn't change, you have the same gap value. Now there is only one node which is unexplored, so we need to number it as 10. And which problem we are solving here? X1 is fixed to 0, X2 fixed to 0, X3 is free, and X4 is set to 0. And when you try to solve this, you see that there is no feasible solution to this problem. This is infeasible, so that's why we fathom. Okay, so in node 10, what happens? We said that in the final node, when all nodes are fathomed, the lower bound becomes equal to your upper bound. So the lower bound is 12, upper bound is 12, and your gap value is 0. So the branch and bound always stops with a gap value of 0. Okay, so this is a complete example of branch and bound for a binary program. And the main difference of this one from the previous case is here we are fixing the values of decision variables. Instead of writing an inequality constraint, we are just fixing its value. That's it. Okay? So we will make more examples in the following tutorials, but please do not just watch these videos, but take your notes, take your notebooks and pencils, and please write down these by yourself as well. In that way, it will be more beneficial and you will understand better. We will continue with our examples. We will solve more examples on branch and bound. But please spend some time on this and try to understand what's going on.